scientist at Bielefeld, and Bern, which is the current position at Switzerland. I think Mikko is really an expert in thermal field theory. So I think so we are all very eager to hear from him. Right.
Okay, thanks. Yeah, thanks a lot. Yeah, it's a great honor and pleasure to be for the first time here. So my topic is thermal phase transitions. And also I was asked to talk about thermal rates. And so it's kind of, let's say, a bit sort of methodological set of lectures. So not so much model building or so, but trying to introduce some tools that we can use then in many different contexts. And so the organization is that I'll start with sort of a hopefully simple introduction to how we can find phase transitions in field theory. Then tomorrow I'll then try to say what we would do today if we really wanted to study some phase transition kind of precisely, systematically. So let's say modern methods. Then one thing which is very important about phase transitions, but is also a bit difficult, is that sort of when one looks at phase transitions in textbooks or so, then the basic characteristic of a phase transition is like the critical temperature, and if it's of first order, second order, maybe what's the latent heat or so. But in the real world, when we are really trying to make physics out of the phase transition, then somehow there is a lot more is going on than these simple textbook things. And there's, in particular, there's some kind of a dynamics that's taking place. And so that's always very, very important in cosmology, whatever we do with the phase transitions there. So I will then describe a bit nucleations and dynamics. These phase transitions. Okay, then that's sort of the background, and then we would really like to see how all of this physics can lead to something. And this also has to do then with these thermal rates. So rates are always important. Typically rates are you are producing, like a production rate. You are producing something, or a decay rate, something goes away or so, and rates in a thermal context. And so actually I think that the sort of a nice context of starting to learn about these rates if we talk about also a bit about physics, namely the physics of gravitational waves. Because gravitational waves is nowadays, if one looks at phase transition, that's very often the sort of number one thing that one is looking at. It used to be that the baryon symmetry was number one and gravitational waves was number two, but nowadays, because of just how things are on the observational side as well, this has really become a very important thing. So it's a good context to look into these rates. And then in the last lecture, I'll then go into baryon symmetry. And also I want to say a little bit also about a different but in some ways related topic, which is magnetic fields. That's also something that one often discusses in cosmology in general and in the context of phase transitions in particular. Okay, so of course this is kind of an ambitious program, so we will not go very, very deep into the later sections, but on the other hand, there are other lectures then which are really into these topics, so I hope that I can say something complementary.
You mean primordial magnetic fields?
Yes, yes. Okay, so let's start with phase transitions. field theory. And now, actually, before we go to field theory, just what is a phase transition? So a good example to look at the phase transition is to look at the phase diagram of water. One sees this very often in textbooks, and rightly so, because it's a very rich phase diagram. Usually one plots it with the axis of temperature and pressure. And so it looks like this. There's one line here, then there's another line here. And these are the basic things. Then if one looks at with a microscope, there are a lot more lines here somehow, like with small temperature and very, very large pressure. But let's not worry about that. That's kind of very, very complicated physics. The phases here are, this is the solid phase or solid phases, actually. So different types of ice. Then there is a liquid phase here. And then there is a gas phase here. So our normal experience is kind of here, sort of intermediate pressure, where we have first ice, and then we have liquid water, and then we have water vapor. There's a point here, which is called the triple point. There's a point, special point here, which is called the critical point. And the critical point is a second order phase transition. It's a particular type of a phase transition. These lines that I have drawn, they are then first order phase transitions. And so there are many on this phase diagram. And then there's one more context, concept which one often uses, which is that, as you see here, it's possible to go from liquid water to water vapor by just going around somehow here without encountering any phase transition. And if one somehow goes around and the properties of the matter just change continuously or even analytically, then one can still say that somehow one goes from one type of behavior to another one, but just not abruptly, and this is called a crossover. And so now in cosmology, we usually would like to actually find these first order transitions. These are the most important somehow in our experience. They can do something for us, but then often it has happened in the past that if we work harder and harder, then we kind of drift along this line. And if we work really hard, then we notice that what we thought was a first order transition is really just a boring crossover. This has happened many times. Anyway, but this then depends on the model. We'll come back to that. So what the goal now is not to take water, but just take the standard model or some extension of the standard model and work out the phase diagram. The axis will be different. Temperature will suddenly be an axis for us also in cosmology, but in cosmology, temperature and pressure, they are kind of not independent variables. For water, they are independent variables because there is basically, you can relate the pressure to density or to some chemical potential. In cosmology, we don't really, chemical potentials are very, very small. So basically temperature is the only thermodynamic variable. We cannot separately talk about another independent pressure, but instead we can replace this axis by something else, like some parameter of the model, like the mass of some particle or some coupling. Okay, so basically this is the goal. Given any model of particle physics, how to map out the phase diagram with some axes and how to find out if there are phase transition of this or that kind. So now to get a bit in that direction, let's start from the simplest thing we can imagine. And the simplest thing we can imagine is the harmonic oscillator. So we start doing thermodynamics of the harmonic oscillator. Okay, so what we would like to do in basic statistical physics, normally when we do thermodynamics, is the first thing we want to do is we want to compute what we call a partition function. I'll denote it by z, and z is formally then trace e to minus beta times the Hamiltonian. For me, well, beta is 1 over t. In maybe statistical physics textbook, you would find here a Boltzmann constant, but I set that to 1. That's just a choice of units. And h hat is the Hamiltonian. And now for the harmonic oscillator, of course, the Hamiltonian then is very simple. P squared kinetic energy and then potential energy. Okay, so now for us, it's useful to write this Hamiltonian. Well, this is one form, but then as one learns in basic quantum mechanics, one can also write it in another form by introducing the creation and annihilation operators. And so then it becomes h bar omega a dagger a plus 1/2, where a dagger is a creation, a is an annihilation operator. And this is a nice form because this is a number operator, so it tells immediately what the spectrum is of this Hamiltonian. Well, we'll need both forms in the following. I denote this combination h bar omega. That's the energy, has the dimension of energy like the Hamiltonian. So I denote it by sort of small e or epsilon or whatnot. Okay, so now for this system, it's simple to compute the partition function because here is a trace. So we have to take some states and then bracket the Hamiltonian with these states. But if we can rewrite the Hamiltonian this form where the number density appears, then it's the problem becomes almost trivial if we evaluate the trace in the basis of the eigenstates of the number operator. And the number operator has then eigenstates which are numbered from 0 to infinity. And these are the eigenstates of the harmonic oscillator. And since these are eigenstates of the Hamiltonian, then it's just sum of Hamiltonian acts on this. It gives minus beta times what I get from here. H bar omega number density gives the n. And this is my epsilon. And so now this sum I can do. There is one constant upstairs minus beta epsilon over 2. And then there's a geometric sum. So e to minus beta times epsilon to power n. So the geometric sum I can just sum it is 1 minus e to minus beta epsilon. So partition function is simple. What we usually want out of the partition function is what we call the free energy. So free energy is then a reparametrization of the partition function. We kind of write it in a sort of similar form as here, as e to minus beta, but then no longer any quantum mechanics or any trace, just the result. We write the result here. This is then the free energy. So free energy is the log of the partition function and minus t. That gives me the free energy. So now I can do this. I can take my z. If I take the log from upstairs, I get minus beta e over 2. And then if I take the log from downstairs, I get minus, because it's downstairs, minus log 1 minus e to minus beta times e. And so now let's just multiply everything together. T times beta is 1, minus cancel, so e over 2. And then there's a minus and minus a plus t times log 1 minus e to minus beta e. Okay, so that's a very important formula, and we will need that formula many times in the lectures. Okay, so now before we go on, I want to also evaluate another quantity for the harmonic oscillator, and that maybe one doesn't see quite as often in quantum mechanics, but it's really central for field theory, and that is what we would what we may call the propagator. And since oftentimes one doesn't discuss it in the harmonic oscillator context, maybe I put it in kind of parentheses. But what I mean by the propagator is really sort of in field theory, what the propagator would be, we would have some field, like some phi. If we use our canonical quantization, we would have some phi dagger field. And now what we do in harmonic oscillator, we don't have any phi's there, but we have x's and p's. And actually x is kind of the analog of phi. And p is then the analog of phi dot. That's the corresponding momentum. So it really, in harmonic oscillator, if we want to compute this kind of a 2-point function, that's sort of the propagator, that's the expectation value of x squared. And the expectation value of x squared means, now in thermal physics, it means that I take the trace, but I put x squared here. And then I take the same weight, and then I normalize it with the partition function. So let's compute this quantity. It will be very, very nice and very illustrative. How can we compute it? Well, there's a simple trick to compute it, and the trick is that now I don't use this form, but I go to this form, because there I see exactly what I need. I see the x squared. And so this means that I can get this expectation value by taking log of trace e to minus beta h hat. And now if I take a derivative of that with respect to omega squared, if I take a derivative, then first of all there's a log, so this goes downstairs, that gives me this. Then there's the inner derivative of this, so exponential remains exponential. And then I get minus beta, and then the derivative of h with respect to omega squared. So I can cancel the minus beta by putting here minus t. And if I take derivative with respect to omega squared, I get exactly x squared, except that I get also an extra m over 2. So I have to also cancel that m over 2. So I can put here 2 over m. Okay, so now I see what I have. What I have here, I take this minus t here and I put it here, because then it's just my free energy. Minus t times the log of the partition function is the free energy. And here I rephrase this in terms of my epsilon. So I multiply this by 2h bar squared over m d f d epsilon squared. Okay, and now it's a simple exercise. So d epsilon squared is 2 times epsilon times dE. And so 2 cancels against 2. I have h squared divided by m. Then I have 1 over epsilon. And then I have the derivative of the f with respect to epsilon. We have the f here, so it's easy to take a derivative. If we take a derivative here, we get 1/2. And if we take a derivative here, we have to, well, watch out a little bit. Again, a derivative of log gives me 1 minus e to minus beta epsilon. Then I have to still take the inner derivative. There I get minus e to minus beta e, and then still the derivative, which gives this minus beta. Minus beta. So now we see that the minuses cancel, t cancels against beta. And what am I left over with? Fortunately, have to go back, but what we get then is that this x squared is some trivial factor, h squared over m, 1 over epsilon 1/2 plus what? So now, of course, I can multiply both upstairs and downstairs by e to beta e, and the minus signs cancel, t and beta cancel, so what's left over then is 1 over e to beta e minus 1. Okay, so it's a very important structure here. We see this is the Bose distribution. I denote it by n Bose of energy E. So maybe in quantum mechanics, one doesn't think of the harmonic oscillator as being a boson, but a boson it is. And we get the Bose distribution. We don't need relativistic quantum mechanics to get the Bose distribution. It really comes from the harmonic oscillator. Also, of course, if one takes a harmonic oscillator, which is then a little bit less trivial, where one, instead of these normal operators, one introduces fermionic operators, anti-commuting operators, then one can also derive the Fermi distribution this way. So it's really all there in the harmonic oscillator. Okay, so this is also very, very, very important. We'll come back to that. Okay, good. So that was the harmonic oscillator. And so why did we do it? We did it because if we take free scalar field theory, then that is really nothing but a collection of harmonic oscillators. And what I mean by this statement is that I can immediately write down now the partition function for a scalar field theory. I denote this by z phi. Phi is my scalar field, and this scalar field is now some scalar field. It doesn't need to be the Higgs field or any known scalar field. It's really like a toy model for us for the moment. And so what I really need to do is I just take a product over all momenta k that this field can have, and each momentum mode is then like a harmonic oscillator. And so for each momentum mode, I get minus 1 over t, and then the free energy of the harmonic oscillator. The free energy of the harmonic oscillator is there, and I write it now. I introduce the index to the epsilon k. So there's this part, and then there is t times log 1 minus beta ek, where now my epsilon k is then the usual energy of a relativistic scalar field. So now here then relativity plays a role. I'm now in a field theory, I'm taking a particular Lagrangian which does respect Lorentz symmetry, and then I get the usual relativistic form. But this form is independent of the system pretty much. Okay, good. That's the partition function. However, as usual, we don't really know what to do with the partition function. We rather like to take the free energy. And so let's do the free energy from there. Well, actually, we can evaluate the free energy, but now in field theory, it's well, the free energy is extensive. It scales with the size of the system. Like in field theory, I mean, there are infinitely many degrees of if you go to a large volume. So it's an extensive quantity. It scales with the volume. So in field theory, it's always good to divide that by the volume. And I denote this by a small f. But otherwise, it's just that I need to take a log out of that. So I have 1 over volume, and then I take a log of a product of exponentials. But the log of a product is a sum of logs. And each term into some log exponential gives just the argument here. So it turns into a sum of k's. And then here I have f, this was a z. And so I have, to get the f, I also have to, not only do I take a log, but I also multiply by minus t, and that cancels this t. And so I get the sum of these terms. Okay. And then here we are still in a finite volume. Now, so now usually in field theory we take the thermodynamic limit at the end of the day. Well, also the universe is pretty large, so it should be a good approximation to take a large volume limit. That said, somehow in theoretical considerations, volume is often a very useful tool. One can learn a bit about the system by keeping a volume finite for a while. So we'll come back to that at some moment. Still, we might go back to finite volume for a short while later on, but at the end of the day, we take the infinite volume limit. Then one should learn in quantum mechanics that if you have this kind of a sum divided by volume, if you take the infinite volume limit, that goes over into an integral, where my integral is just the usual d3k 2 pi cubed. Okay, to show this, one has, well, the simplest way is to take a periodic box, and then one sees that in a periodic box the momenta are discrete, but the discreteness is related to the size of the box in such a way that if you take the infinite volume limit, the volume from the discreteness and from here they just combine in such a way that you really get this continuum integration measure. And then the same thing. Okay, so now let's look at this this term, and well, there's one part here. Let's say part A, and then there's a part B, and the part A is completely independent of temperature. So it's a vacuum term. And also, it doesn't look very safe, so to say. I mean, we are integrating overall momenta, and the integrand grows with the momentum. So clearly, this is not even defined in as such, literally. And so this means that to deal with this first term, one has to really first regularize the theory and then think about renormalization. And I mean, this is an important and nice exercise in itself, but it's not really what we are doing in this lecture. So therefore, we will not touch this part of the exercise. The second part is much nicer because this part is really convergent. This integral is convergent. It's convergent because here is e to minus beta ek, and when the momenta become large and the energies become large, e to minus energy becomes extremely small. Log of 1 minus extremely small is extremely small. It really converges exponentially fast. I denote this this part by the thermal part of the free energy, and it's a function of the mass. I mean, we are integrating over momenta, so momenta vanishes, but it's a function of the mass. Okay, so let's discuss a bit this function, some values of this function. So one thing we could discuss is what happens if temperature is very, very small. Can we evaluate the integral in that limit? Well, in fact, in that limit, the integral can be evaluated, because if temperature is very small, then the energy over, here appears energy over temperature. This is always larger or equal to m over t. And so this is then much, much larger than 1. And so then e to minus ek over t, this is much larger than 1. Therefore, this one is much, much smaller than 1. And therefore, ln 1 minus is, to a very good approximation, is the first term in the expansion. So it's minus beta ek, and therefore this function is tk minus tk e to minus beta ek, and this is an integral that one normally does in the first course in statistical physics. In fact, we saw the answer for this integral this morning in the first lecture, where Misha called this integral basically the number density. So this is this very well-known mt over 2 pi 3/2 e to minus m over t. Well, actually, it's an approximation still, but it's an approximation valid in this limit. And so what one sees is it's really exponentially small. If m over t is large, then this is exponentially small. It's negative also. Good to notice. So now let's look at the other limit. And the other limit, m much less than t, how would you do that? Well, maybe the first thing that comes to mind is one looks at this, it's an integral, it's a convergent integral, and there is m squared here. So why not do a Taylor expansion in m squared? Sounds reasonable, or to be precise, m squared over t squared then. Well, it turns out that, well, it's a very good idea. It turns out that this is extremely delicate. And the reason that it's extremely delicate is that actually one can learn, we'll see, we will even learn in this, maybe tomorrow, we'll see it already today. But what we will learn is that if one would plot this, if one imagines that this m is a complex parameter, and implicitly it's a complex parameter if we are talking about some analytic series, then actually in the complex plane of this m, this function it's a branch cut here, ending at 0. And so now if we would do a Taylor expansion in m squared, which means that we would be Taylor expanding around this point. So any mathematician can tell you that don't do it. But physicists are not mathematicians, so we still do it. And it's an extremely interesting structure which appears. And so tomorrow we'll kind of see how one can actually derive it. But today I will just show what comes out. So maybe I should say that strictly speaking, does not exist. I don't know how to say it, does not exist, but still maybe as an asymptotic series or so, let's see. But formally, one can write the following: that in this limit, there is a term, a very famous first term, minus pi squared t to the 4th over 90. Well, why is it famous? It's famous because that's the Stefan-Boltzmann law, basically, of massless photons. Makes sense. If mass is 0, it's like photons. Then there is a correction. So it starts nicely. It starts as if it were a Taylor series with a correction of m squared. But then the next term shows that there is an issue because the next term is really has a branch cut. We often write it as m cubed t over 12 pi. But here really m is, I mean, in my problem, there's no m as such. The parameter is m squared. That's the parameter. So if I write m, I mean square root of m squared. And so this is m squared to 3/2. That's a term which has a branch cut. But still, it somehow, formally, it is somehow smaller than this one. And so it goes on. Then there's also another non-analytic term. Okay. So that's kind of, now I mean, I was sort of trying to say that this expansion has some problems, but actually, I mean, for a physicist, it doesn't have any problems. It's really a beautiful expression, very nice to derive, and has lots of physics in it, despite what a mathematician might say. Okay, so that was analytics. Then there's a third thing we can do. We can just evaluate this whole thing numerically. It is really convergent. One can put it in Mathematica, and in a fraction of a second, one gets a nice curve. And the curve looks like this. I plot it as a function of m over t. I put here some numbers which look maybe a bit weird at first sight, but they are kind of easy to remember, like pi and 2 pi. But these are just like some, we could equally well put here 3 and here 6. It's not, there's no, for the moment at least, there's no deep reason why I put here. Anyway, it starts with this famous value here. Then indeed it starts going up with a curvature, and then somehow it goes, and then at the end it approaches 0 very, very fast, according to this this form here. It's exponentially close to 0. Okay, so that's the function. The function exists. If you are not comfortable with the analytic expansions, you can always use the numerical evaluation. For practical purposes, it doesn't matter. You don't need to do analytic things. For us, these analytic things turn out to be useful, but that really the function is a simple function. And what it means is that small values of mass are somehow favored in a thermal system. Their free energy is lowered. They are preferred. They carry lots of entropy, we sometimes say. That's why they go down here. Okay, so these are the things that we need now to discuss then a phase transition. And perhaps before we go there, I give some kind of a bit of a teaser or an exercise or something that will then come back to us, but well, what I want to do is, we had this propagator. The propagator had this form, 1 over Ek, then the vacuum term, 1/2, and then the Bose distribution. Looks very simple, looks very nice, But surprisingly, it's not always the best way to write this expression. And there's an alternative way to write this expression. And the alternative way at first sight looks more complicated because it's a sum. But then it turns out to be sometimes very useful. And the sum is the following: sum over all what I call omega n squared plus ek squared, where omega n is 2 pi n times t. N is a positive or negative integer or 0. These omega n's, these are known as the Matsubara modes. Or Matsubara frequencies. And so this expression can be proven, and it's not completely trivial to show it. And I can give you a hint of how to show it. It's a nice exercise. One can consider that function, the following function. I take omega squared, sort of similar to here, but like I put here omega squared plus ek squared, and then I multiply it by both the distribution, but as a function of I times omega. It's no physics at first sight. It's just a function. And now I plot this function in a complex plane. And I ask, where are the poles? So from the denominator, there are 2 poles. There's a pole here, plus I times ek. Another pole here, minus I times ek. These are the poles from the denominator. But this Bose distribution also has poles. In fact, when I put here an I, it turns out that it has poles along the real axis. And, well, infinitely many of them. And now the trick is the following, that I take a contour here. I draw a line here. Well, I draw 2 lines. One line here, another line here. So now I integrate this function along these lines. And then I can do 2 different things. I can use the Cauchy theorem, but I can use the Cauchy theorem either such that I close this contour up here, then I pick up these poles, gives me one expression, or I can close the contour here, gives me another expression. Then I can use the Cauchy to close the contour around these poles, gives me another expression. If I close along these poles, I get this form. If I close along these poles, I get this form. A very nice exercise in complex analysis. Okay, I think we are about halfway, so maybe a good time to ask questions. There was.
Yeah, it's all like the time of propagators, right?
So does this have anything to do with the Feynman prescription for calculating the propagators in QED?
Yeah, it has a lot to do with that, but it's not exactly the same because this is sort of like Euclidean. There are no minus signs here, no I epsilons or so. Everything is on the real axis. I mean, if this is real and this is real, there are no zeros. Whereas Feynman propagator then has zeros, and then there is a prescription of how to avoid the zeros. So in some sense, it's simpler, but it has the same structure. It's kind of an analytic continuation of the Feynman propagator.
Thanks.
More questions?
When you did the Taylor expansion for FTM, you put only one term.
Here? No, there are.
The other one.
This one.
Yes.
Yeah. Right. These are. So there are more terms. Yeah. So
if I expand, the only thing that's changed is here the approximation of the curve.
Yes, yes, one can, actually this is also, one could talk, I mean, there are many ways to, well, yes, one can discuss what kind of corrections there are, and I showed the simplest one, but this is already pretty good, but then one could do other, for instance, one can expand this in terms of some Bessel functions, then one gets a kind of well-convergent expansion here, or one does something else and then it's not so well, but I mean, it really works well, it works kind of here, it works well here.
And is enough to argument.
It's enough to
To
it's enough to show that this goes to zero very fast.
yes.
If we want to know how it deviates from zero, then we might, in some cases, we might want to work a bit harder.
It's enough.
But if we just want to look at the expression as a whole and we are interested, it's sufficient for us to see that it goes to zero, then the leading term shows that it goes really very fast towards zero.
Okay, I think you can go ahead.
Okay, so now we go on, and now because I want to achieve something today, I'll just state something here. I state it kind of as a recipe, but we'll come back to that then tomorrow, and we'll prove it. And what I call is recipe of imaginary time. Formalism. And so what I mean by this is that if we now wanted to look at the scalar field theory, but maybe we don't want to look at anymore at the free theory, but like introduce interactions and compute the partition function even in the presence of interactions, then we can write down some sort of a path integral for the z, for the partition function. And the path integral looks like path integrals do, except that in this case, often in the path integral, as one learns in quantum mechanics, there is an I, but in this case, what you call imaginary time formalism, there is no I, there's a minus. And then there's a minus, what I call Euclidean action of the phi. And then in this path integral, there is something I call BC, and BC stands for boundary conditions. It's a path integral with special boundary conditions. The Euclidean action is an integral over the volume d3x. That's a spatial part. Well, that's what, and then of a Euclidean Lagrangian. So that's familiar. But then there's also a time integral. And now in this imaginary time, the time integral is not from minus infinity to plus infinity. It's over a compact period of a variable which I call tau. So it's something like time, but it's not the usual physical time. And then it's from 0 to beta. Beta is the inverse temperature. And what is the Euclidean Lagrangian? The Euclidean Lagrangian is the Minkowskian Lagrangian. I denote that by L Minkowskian. But there also you have to do something with the time. You replace time by minus I times this other time. I mean, physical time is real, and this other time is also real. It's from 0 to beta. But one calls this the imaginary time formalism because if one writes it like that, then it's really an analytic continuation where it looks like the imaginary unit appears there. But at the end of the day, both are real. And there's a minus here. It's a convention, if you wish. Okay, so if you've never seen this, it looks a bit mysterious maybe, but yeah, tomorrow we start the lecture by showing how this can be obtained. But for the moment, what I want to kind of just remark is that there is of course, there's a relation of this thing to this teaser, and the relation. Well, I should say first that the boundary conditions. What are the boundary conditions? So since this time direction is compact, then basically one has to say what happens at the boundaries. I mean, if you have infinite volume, you don't care what happens at the boundary. But well, you don't. Sometimes you have to care even in that case. But if it's finite, for sure you have to care about what happens with the boundaries. And here the boundary conditions are that the fields have to be periodic for bosons and then anti-periodic for fermions. And so what this means is that if you take a bosonic field like our phi, and you take it at any point x, then if you go to the upper end of the interval here to beta, then this has to be the same as at the lower end of the integral, 0. That's the definition of these boundary conditions. Now, why it's like that tomorrow? But the relation to these Matsubara frequencies is that we can note already that if I imagine that I have a field which I kind of expand in the same way as I had there, T sum over omega n, just like here, and then I do Fourier analysis with this. And then I have some field, some Fourier mode, which is maybe a function of these ones, sits at the position x. Then this term has the same value if I take tau equals to 0, its value is 1. E to 0 is 1, but that's also the value at I omega n times beta. Because beta is 1 over temperature. If I take 1 over temperature times temperature, I get 2 pi times n. E to I times 2 pi n is 1. It's periodic. So indeed, if I have those Matsubara modes, then this periodicity is satisfied. So that's kind of shows that there's a relation. Anyway, for the moment, we take this as a recipe and let's see what we get. So what we now do is we then need one more concept. And the concept is the concept of an effective potential. Well, effective potential is a very important notion in field theory, and it can also be defined in many different ways. And often the definition one finds in textbooks is based on some Lejeune transforms. And somehow it's traditional, but it's not really the ideal for many reasons. There are some hidden problems. For instance, Lejeune transforms, one actually in the definition with Lejeune transforms, one also has to invert Lejeune transforms, and they are not always invertible. And there are also many other, well, some other issues. So I will define it in a sort of non-standard way maybe, but actually this non-standard way is simpler, and there are no ifs. It's really can be done nicely, and the price to pay for this niceness is that now we have to go for a moment back to finite volume, but just for a moment. Okay, so then this means that now I can do Fourier analysis in this volume, in this finite volume. And I denote my Fourier momenta by a capital K. And there is a time component, and this time component is actually exactly my Matsubara frequency. Again, we'll come back to that. And then there are the spatial components. But what the finite volume now does is that the spatial components are also discrete in a finite volume, because the finite volume is finite. You impose some boundary conditions, for instance, periodic, and then there's only a discrete set of frequencies which satisfies these periodic boundary conditions. So now, what this means is if this is a discrete set, then you can single out a special momentum, namely zero mode. It's really separated from the other ones. Zero mode is that both omega n is zero and the spatial is zero. In infinite volume, this is not so. It's not separated because the momenta are continuous. But in a finite volume, this is really a nicely separated mode. And so now I write my field phi as a sum of phi bar plus phi prime, and the phi bar is the zero mode. K is 0, and the phi prime is then that K is non-equal to 0. So at least one of the components, it can be the 0 or the spatial component is non-zero.
Mikko, there's a question I think online. I'm not sure. I will read it. I think Anya, she was asking it means that temperature is a replacing degree of freedom for time in Euclidean space-time, or we just interpret it as an imaginary time.
If you are computing certain quantities like the partition function, then you can formulate it in a way that temperature is Euclidean. I mean, that you have Euclidean field theory with a compact Euclidean time direction. But this applies only to a certain subset of observables. There are some other observables like these rates where things are a bit more complicated. You have to do careful analytic continuation, and you can talk about both imaginary time and then also real time simultaneously. So I don't know if that is exactly the question, but I'm saying that what I'm doing now is sort of for the moment at least for a subset of observables, and for the full set of observables, maybe the path integral is a bit more complicated. You also have to have simultaneously some imaginary and some real time contours in your system. But so if that was the question, then it's a good question. It's a non-trivial answer. Yeah.
Okay. Okay. Thank you.
Okay. So what do we do? So we do the following. We want to do this partition function. We have the recipe, and now since we are able to really cleanly separate the fields into two parts, we also write the integration measure as an integral over this zero mode. And this is a real field, so we can integrate from minus infinity to plus infinity. And then integral over all the non-zero modes. And then in the action, we have to do the same. We write phi as always sum of phi bar and phi prime. Okay, then we will do the following. We imagine that we carry out this path integral. Well, in practice, it may not be easy, but let's say theoretically we can imagine that we carry out this path integral over the phi prime, but the phi bar we still keep as a parameter. So I still have this integral here. And now I write the result for this path integral. I write it a little bit like we wrote previously as a free energy. So I could write here minus free energy over temperature. Actually, I again take out the volume, so I write minus volume times the temperature, and here would be the free energy density. But I don't write free energy density. Instead, I call now the free energy density an effective potential. And this is then a function of this phi bar, because that's a for this path integral, it's a parameter. Okay, now I imagine that we have constructed this. And so then if we have constructed this, we can plot this. And I imagine that I plot this and I find the global minimum of this potential and I expand it around the global minimum. If it's the global minimum, or in fact if it's any minimum, but in particular if it's a global minimum, then the linear term in the expansion drops out. The first term is then the curvature. And then there are high order terms. So now one has to realize that this integral is extremely rapidly convergent because there is the volume here. Volume is, for a moment, it's finite, but at the end we want to make it infinite. It's very rapidly convergent. I mean, it's e to minus some large number times. This term is constant, and then some dependence on phi bar on the integration variable. And so, in fact, this term is constant, so I can pull that term out. And then let's imagine that we carry out an integral. And it's a Gaussian integral. I mean, if I just keep this term, it's a Gaussian integral with some coefficients here. And all that I need to know about the Gaussian integral is that if I have a Gaussian integral, it gives something, maybe pi over square root of the coefficient. And so we get 1 over the square root of this coefficient, and I'll only keep here the volume. That's important. So we get something, let's say, some c times the square root of the volume. Okay, so now we still want to get then the free energy density. F phi is minus T log Z phi over the volume. And Z phi is here. If I take log and multiply by minus T over V, if I take log from here, I get what's here, and minus T over volume cancels against minus volume over T. So the first term is V effective at phi bar min. But then there is not exactly that. There are also corrections. But for the corrections, I get minus T over volume times the log of C over square root of volume or so. So now the volume doesn't cancel. In the leading order, it cancels because there's a volume here and there's a volume here. But in this term, it doesn't cancel. There's only the square root of the volume. So I have a log of square root of the volume minus 1 over volume. Of course, if I make the volume large, this log grows, but log of volume grows always much less rapidly than 1 over volume. So if I now send the volume to infinity, this goes to 0. And so that's why this effective potential is so useful, because if we are able to compute the effective potential, then we need to find its minimum, and if we evaluate it at the minimum, we get the free energy density, and that's what we need. Okay, so that's why one always looks at the effective potential. So now let's try to evaluate this effective potential. And we'll do it again for a toy model. We'll just take a scalar field theory. So I now separate the time components. I write, maybe it's a bit pedantic. dt phi squared minus then the spatial components minus this is the tree-level potential in the Lagrangian. The first thing we need is the Euclidean Lagrangian. Euclidean Lagrangian, we do the analytic continuation and take a minus sign. You see, if I put tau to minus I tau here, then there's an I, and there are two I's, there's a minus sign. So there's a minus sign here, but here was always a minus sign. Here is a minus sign, and then there's an overall minus sign. So in total, this object is very kind of user-friendly. Everything is positive. Everything is positive. Often when we do Euclidean field theory and we have only positives, then we kind of introduce sort of an Einstein convention, but a little bit different in the sense that we put the indices. In the normal Einstein convention, one index is down, one index up, but here we write both indices down. This is sort of an implicit indication that we are in Euclidean signature. Okay, so now we take that, and now let me furthermore specify the form of the potential. And I take a potential, of very much the same sort that we saw in the previous lecture, namely some kind of a symmetry breaking potential. So I'll put here in the potential, I put minus 1/2 m squared phi squared plus lambda over 4 phi to the 4th. But I'm just doing now this with a real single real scalar field, so it's not. It's really extremely simplified setup. Okay, so what we have to do now is we have to make this replacement. And so let's look at the different terms. So I have to write phi is phi bar plus phi prime. So what happens? If I take the kinetic term, then the phi bar is a constant, so it doesn't give any contribution. So I get only a contribution from here. And so I write it like, I leave some space, I put it like here. Then I take minus 1/2 m squared phi squared. So now I get 3 terms. Minus 1/2 m squared phi bar squared minus m squared phi bar phi prime minus 1/2 m squared phi prime squared. And then the last term plus lambda phi to the 4th, plus lambda phi bar to the 4th Then 1 phi prime gives a factor of 4, so plus lambda phi bar cubed phi prime. Then if you have a 4th power and you take the middle term, then there's a factor of 6 there. And there's a factor of 4 here, so in total it gives a 3/2 lambda phi bar squared phi prime squared. And then there is again a factor of 4, so lambda phi bar phi prime cubed and 1/4 lambda phi prime to the 4th. Okay, so these terms are simple. There's no no dependence on spatial. This phi bar is a constant. It's constant in everything. It's constant in time. It's constant in space. It's really a constant. No dependence on coordinates or anything. So independent of tau and x. Then there are these terms which are linear, which have some powers of phi bar, but then they are linear in phi prime. So I claim that if I integrate over them, I get 0. Why is it 0? Well, because these phi primes, remember they? Okay, it's no longer it. The phi primes are the ones which have non-zero 4 momentum in at least one direction. So they are oscillations. So if I integrate over the oscillations, I get 0. Put another way, if I integrate without any weight over phi, then that's a projection on the 0 mode. That's just the Fourier transform with weight omega n 0, so that e to I omega n is 0. So this is a projection on the 0 mode, but by definition, phi prime has only the non-zero mode. Therefore, the average is 0. But it's really because this is oscillations. So these terms drop out. And these terms, so that's very, very important. These terms drop out. Then these terms, the dependence on the phi prime, that's the one which is kind of a fluctuating field. It has dependence on time and x. It's quadratic. It's like a free theory. But there's a coefficient which is no longer the one from the Lagrangian. It has been modified by this term. So this is one, we can write it as 1/2 m effective squared phi prime squared, where m effective squared is minus m squared plus 3 times lambda times phi bar squared. And then these terms they have 3 phi primes or 4 phi primes. So we call, these are then interactions. There's a vertex. There's a vertex like a cubic vertex, or there's a quartic vertex. These are vertices. But this is not a vertex. This is just a modified mass, but the mass which now depends on the background. Okay, so now with this, what do we want to do with this? Well, what we want to do with this is basically we want to now evaluate the effective potential. So we want to do this thing here. So let's write. Let's write it again. So we have this e to minus v over t v effective of phi bar is the integral over these d phi primes, e to minus, and then I now write here d tau volume d3x And then I collect the terms that we found out. And the first terms are, the first term is just like the tree-level potential, the potential from the Lagrangian, but evaluated with the phi bar. Then the linear terms drop out, and then there is a term which is, then there are the terms, this term and this term, which is like a free scalar field theory. I maybe put it like sort of in. And then there are the interactions, and I leave out the interactions. And now we can do this. Well, the first term, what is the first term? It's constant. So this integral gives me just, for the constant, it gives me volume over temperature. It gives me exactly the same as here. So this is e to minus volume over temperature times tree-level potential with phi. And then there is like a path integral, but this path integral is exactly what we did with the harmonic oscillator. So it is exactly what we did with the harmonic oscillator. It is minus v over t f phi, what we called f phi with the harmonic oscillator, but the only thing is that the mass is not the Lagrangian mass, the mass is this shifted mass, m effective. And then there are further terms, and let me write them like this. And if we take then the log, then we say that V effective phi bar is, well, the Lagrangian. Sometimes we may also call this the V effective of 0th order phi bar. Then there is this term f phi m effective, which we call the one loop correction to phi bar. And then there are further corrections. Okay, so now we are almost done, because now we can take then what we learned about this f phi. We learned something about that, so recall. And now I take this, we could do it numerically. We could get the same conclusion, same result, but instead I take this sort of a little bit adventurous high T expansion, Taylor. And the Taylor would say that this one was minus T minus pi squared T to the 4th over 90 plus M effective squared T squared over 24 minus M effective cubed T over 12 pi, and so forth. Okay, so let's look at what these things do. So let's now try to, this is important, so let's try to be careful. So again, I write maybe now the tree-level term explicitly here. Once more. And then we ask what comes out of these corrections. Okay, so first term minus pi squared t to the fourth over 90. I mean, it's the dominant term, so surely it's important, but it's completely independent of the phi bar. It doesn't change the shape of the potential. So it's a constant. So actually, like when we are looking for the minimum or so, somewhere we were looking for the minimum, then it doesn't matter. There we only need the shape. Well, the next term has a dependence on the phi. So mf squared t squared over 24 is minus m squared plus lambda 3 times lambda phi bar squared 24 t squared. And now you see there is phi bar squared here. This term is constant. But this term is not. And let's sum together these two. Let's sum together these two, then 0 plus 1. Well, I'm now only, so far I'm just keeping one term. So there are constants, and then now there is plus 1/2 phi bar squared, and there is from here there is the minus m squared, and from here there is 3 over 24. It's 1 over 8, and I take 1/2 in front, so 1 over 4 is left over. So lambda t squared over 4. And then there is 1/2 lambda phi bar to the fourth. And so what we see now, this is then really like the starting point of the study of thermal phase transitions in field theory, is that we see here that this symmetry breaking, this negative minus m squared, it's corrected by a positive term. And if the temperature is high enough, then this curvature term is positive. Curvature becomes positive if we say T is larger than critical temperature, where the critical temperature we can solve just by equating these terms, and the Tc is then what? It's 2 times m over square root of lambda. So it's really, well, that at low temperature we have this plot from the standard model, and then at high temperature the curvature term is positive. Okay. So now I want to do one more thing. Let's see what happens if we include this term.
I mean, when one is doing this sort of simple analysis, also in the context of BSM models, I mean, even when you take the full integral for the thermal term, I mean, there's always this issue where you reach this branch cut, right, for small field values.
Yeah, we'll come back to that tomorrow.
Oh, you'll talk about that, okay.
Of course.
I was wondering how worried I should be about that.
No, I mean, it's an important point, yes.
Yeah, okay, thanks.
Mm-hmm.
And so, what would happen if I include the interaction terms?
What would happen? Yes,
Yeah.
a very good question. Yes, I'll kind of come back to that in just in a few minutes. Yes.
Okay, thank you.
Yeah. Okay. Good. So let's now first finalize this by asking what happens if I keep minus mf cubed t over 12 pi. Now this is a bit complicated because this is non-analytic and square roots and stuff. So I'll simplify life by just to illustrate what might happen. Simplify by setting. I set this tree-level mass to 0, and let's just see what happens. So then, and now I sum these two, but including this term. So what I then have is I have 1/8 lambda t squared phi bar squared. Then I have this term, so 12 pi minus t over 12 pi. And then m effective 3/2. So let me write m effective is then minus m squared plus 3 times lambda times phi bar squared. So let me write 3 lambda 3/2 phi bar cubed plus lambda over 4 phi bar to the 4th. And let me try to plot this somehow, just like what does it look like, roughly speaking. I plot it as a function of phi bar, and I plot this approximation. And so it looks like a polynomial. This term is not really non-analytic, but it looks like a polynomial. And so if you have a polynomial, then at the smallest values of the field, the smallest power dominates. And so it's positive. So we go up. It's like positive curvature. Then if you go to larger values of phi bar, then this term becomes important at some point. But it comes with a negative sign. So it says that it somehow starts turning down the potential. But then if we go to very large field values, then the highest power of phi bar wins. And then it goes up again. I'm assuming that this lambda is positive. Then it goes up again. So now this is what historically made people very excited, because what this looks like is like you have really two degenerate minima. So there's this one minimum here, and there's another one. Well, here they are not degenerate, but assume that we kept this m squared non-zero and tuned it somehow appropriately, then maybe we would find a value of the temperature where actually these two minima would be degenerate. And this would be an indication of a first-order transition, a discontinuity in something. In this case, phi bar, but then also in physical quantities, which you can derive from that. If you had something like that, then in particular, here would be the phi bar minimum at large temperatures, and all of a sudden it would jump to somewhere else. And if and the value of the potential here is the free energy density, and so then you really have different functional behaviors of the free energy density because they come from different parts of this function, and this would give you a first-order transition. So now comes the key question. The key question is that all of these things, actually the restoration of the symmetry, but also these funny features that we saw there, they came from this one-loop correction. And so this means that the one-loop connection is important. We have tree-level potential, then we compute something, we get a very large effect, like a qualitative change in the properties of the system. So we have a question. If V effective 1 is very important then can be effective larger than 2 be neglected. And the answer is in general no. And and in fact, in lambda phi to the 4th theory, okay, lambda phi to the 4th theory is a very, it's for us it's always the simplest toy model, but at the end of the day, if somebody starts really studying it like rigorously, then it's not at all simple. It was a question of triviality and many other things, but in some sense, in a pragmatic sense at least, we can say, in fact, in lambda phi to the 4th theory, there is a transition, so that is okay. But it is of, in this case, it is of 2nd order. So in particular, this indication that we saw here that something like a 1st order signal could emerge, that turns out not to be correct for this theory. And so now that's clearly very important. And so that's then where we stopped for today. And so tomorrow we then go on from here, and I'll try to then illustrate you a method where we can kind of study these systems reliably and see if there really can be a 1st order transition. And then I can give examples where there is no 1st order transition, but also other examples where there really is a 1st order transition, which could then be interesting for cosmology. So,
okay.
Yeah.
Thanks, Mikko, for a very detailed lecture. We have plenty of time for questions.
Sorry, going back to the harmonic oscillator, could you compute the expectation value of the number operator? Because I think there's a divergence in the sum. Should be a product of n times the exponential.
But the exponential is e to minus n also.
So the product of n times this exponential, it's not divergent, you think?
No.
All right.
Thank you for the class. I have one question. In quantum field theory, usually when we have some kind of path integral, we resolve using an approach that the field is the classical field but plus a perturbation. Some kind of technique give the same structure that you obtained?
Yeah, this is what I think what you refer to, or one example of what you refer to is a semi-classical expansion.
Yes.
And it has some similarities with this, but it's not exactly the same. I mean, yeah. But yeah, they are related. I think one can say that they are related, yeah. You can, in some sense, often people think about this phi bar as a classical background. But for me, it really had a concrete meaning where I didn't need to say what's classical, and it's really the zero mode of this. So, yeah. But these are fine differences. So I think it's, on the first side, it's very much related, yeah.
But if I want to do the expansion using this, I will obtain the same answers than you? I
think to this order that I showed today, yes. I mean, then of course, at the end of the day, we really have to, in the semi-classical, if you really have a semi-classical around some non-trivial configuration like an instanton or so, then one can compute the classical action and then maybe with very hard work, the one loop correction to it, but it's very difficult to go beyond that. But in our problem, it's essential that we go beyond that we really can treat all orders and we don't need to stop at the fluctuation determinant.
Thank you.
So you provided us with thermal corrections to mass in lambda phi 4, but you did not talk about quantum corrections with one loop diagrams, for example. So I think that in the end, the full theory, you have to sum both contributions. But I'd like to ask if the thermal correction would be much more important when we have phase transitions than the quantum corrections, or there is not such thing?
No, I mean, so see, the quantum corrections are in the term, but I kind of omitted in the beginning. But I mean, if you then do like a real study, like state of the art of some concrete model, like a standard model, then of course you have to include the quantum corrections, you include the thermal corrections. At the end of the day, there are points where the quantum corrections are very important also. For instance, it's in the standard model, the quantum corrections are very important to the Higgs self-coupling from the vacuum loops from the top are very large and so forth. So, I mean, at the end of the day, you have to include just do a good job, renormalize the theory somehow, then include all the corrections and yeah. And the methods that one can use for that, including all types of corrections, these are also like a bit like what I'm then showing tomorrow.
So can I consider what you call mass, the renormalized mass from?
Yeah.
All right.
Yeah, it is a renormalized mass, but in some then okay, if you say renormalized, then the question is renormalized how precisely, like with scale and whatnot. So you really have to, you first choose, like, let's say you could do something like this. You could first choose the MS bar scheme, then the parameters I showed would be MS bar parameters, but then you do one computation where you relate the MS bar parameters to some physical parameters like pole masses or so, including loop corrections. And on the other hand, you do a computation where you use the MS bar parameters and express thermal prediction in terms of the MS bar, but then you can relate the thermal prediction to MS bar to physical, like to pole mass. Okay. Then you have physical thermal prediction in terms of physical quantities, and the intermediate step, like the MS bar, is just like a tool. This is often what one does then in practice, somehow to separate a bit these two steps. But at the end of the day, you really have to express physical quantities at finite temperature in terms of physical quantities at zero temperature.
Thank you.
I have a very basic and general question. To explain baryon asymmetry, there are these Sakharov conditions, and are those conditions stated at zero temperature? Or in other words, what is the role of temperature for discrete symmetries?
Yeah, I mean the Sakharov conditions, in principle, they can be stated at any temperature, but I mean normally they are applied at finite temperature. And we'll come back to that also a bit later on, also in my lectures, I think also in many other lectures. I mean here somehow in the Sakharov conditions, the beauty of them is that they factorize the different ingredients into separate ingredients. And sort of what I'm discussing, in the end, what I'm discussing today is most important not for the discrete symmetries, but rather for the deviation from equilibrium. That's one of the Sakharov conditions. That's sort of what the phase transitions do in the first place. But then at the end of the day, they can also address maybe the other conditions somehow, and maybe we'll come back to that later on a little bit. Yeah.
Any other questions?
So, twofold question. The first one is this last statement is completely general. It holds at all orders.
Yeah.
And what is the crucial ingredient that if I embed lambda 5 to the 4 in a larger theory which gauge interactions, instead I can have a first order phase transition?
Yes, exactly. Basically, you have to have, I mean, normally you have to, I think, this is not a rigorous statement, but kind of empirical statement is that you have to have at least two couplings. If you have two couplings, you can play with the coupling such that you find a regime where you first of all find a phase transition, and you can arrange such that the expansion parameter is small by having some kind of a hierarchy between the couplings. This is, I think, the simplest way of organizing this.
So the crucial ingredient is having an additional coupling.
And often this is an additional gauge coupling, but it can also be just two scalar fields with funny couplings that can already be used to do a first order transition.
Thank you.
Anything else from the audience? Yes. So, okay, I think continue Enrico's questions. So in this case, if we include the mass term, so it doesn't help? Or?
No, the mass term doesn't help. Here it doesn't help, yeah. It doesn't change the conclusion, yeah.
Okay. Okay, I think we can go for early coffee break. Okay, thank you.